So what we're going to be doing today is again a solids of revolution, and we're going to be using what are called washers. And I'll explain with a picture in just a second what I mean by washers. It'll be pretty clear once you see the picture. Um, the general idea is that we're going to have two curves when we're finding our volume, and then we're going to rotate not the whole segment from, say, down, up here down to the bottom. We're going to look at cross sections like this. So between the two curves, and then we're going to rotate that around the x-axis like we had been. Let's see, get a picture for you. So before, we got solid shapes like this one when we rotated around the x-axis. But what's going to happen now is we're going to have a gap. So there's a space here between the x-axis and my bottom curve. And what happens is we end up with something more like this. And I can put in a little bit more. So this three-dimensional shape actually has a hole through the middle of it. So it's something like a bead on a string. So you can imagine the x-axis is a string going through the center of this shape. And what we want to do is be able to find the volumes of things like this. So not just totally solid things, also things with holes in them. And our method is going to be exactly the same as before. We need to find the area of cross sections and then integrate those. And I have the start of our formula at the bottom of the page. So we're starting in the same place, area of the cross section, and then integrate along the x-axis from A to B. But what we need to do now is imagine what a cross section would look like if we took a plane and just sliced through. We're not going to be getting disks because there's a hole in the middle. What we're going to get is, well, a washer. So there's an outer disk with a hole punched through the middle. So the outer circle comes from the higher function, and the inner circle is going to come from the smaller function. And we need to find the area of one of these. And what I want to do is look at this shape, and we can see that there's actually two circles here. So there's a bigger circle, and I'm going to label that bigger radius with a capital R. And then there's a smaller circle, this one, label that radius with a smaller r. And if we want the area of this region, the simplest way to do that is take the biggest area, the area of this whole circle, and then punch out this little bit by subtracting off the smaller area. So what we get is pi capital R squared, that's the bigger circle, and then we subtract pi little r squared. So we have the big area and we punch out the small area. And that's the idea. And maybe going back to this original picture, this higher function f of x is going to play the role of the outer circle. So we usually label that with a capital R. And then g of x will label with the lowercase r, since it corresponds to the radius of the inner circle. And then we just put that together with our volume formula. We plug this in here. So both of these terms have a pi. I'm going to write that first. And then in parentheses, I'm going to have the capital R of x squared minus lowercase r of x also squared. Okay, and that is our formula. So we've taken our cross sections, which look like washers, like a disc with a hole punched through the middle. We found the area of each of them, and then we're going to integrate all of those areas to get the total volume. So we're going to add up all of our little slices to get a volume. Any questions so far? Before we actually get to an example? Okay, so here is my first example. We're going to be looking at a region bounded by two curves. The first one is the parabola y equals x squared plus 1. And the second curve is the line y equals minus x plus 3. So we're going to take the region formed or bounded by these two curves, and then we're going to revolve it around the x-axis, just like I did in my picture earlier. So the first step, we're going to have to graph both of these functions. And the reason that we really have to start by graphing is, well, we don't know which function is on top. Because it matters. We need to know which radius is larger and which is smaller. So we definitely have to graph these things. Luckily, these are pretty simple. We have a parabola, a very simple parabola, x squared plus 1. And you can graph it by plugging in a few points. If you plug in 0, you get 1. If you plug in 1 or minus 1, you'll get 2. And if you plug in 2 or minus 2, you're going to get 5 out of the formula. And once we've plotted these points, we can get a pretty good graph just by connecting the dots. If we wanted to be maybe a little bit more precise, we could, find where the vertex is using a little bit of calculus, but it's pretty clear from the picture because it's a simple parabola. And the line also is a pretty simple one because we can just read off the y-intercept to be 3 up here, and then the slope is minus 1.
Sorry, I don't know that, but I do have a skill you might like.
And there's my
song that never ends.
echo responding. I'm going to go mute that. Give me just a second. Okay, so graph your line with slope 1, slope -1, excuse me. Like so, and then maybe we can label both of these. So y equals x squared plus 1 for the parabola, and then y equals minus x plus 3 for the line. And now we have a pretty good picture, and since these curves are, well, they were chosen by me to make this example, so I chose them so that we could actually see where the intersections are. Because these intersections are going to form our bounds on our integral, because we need to know where to integrate. So maybe I can do it this way. This is our region bounded by the two curves. And what's going to happen is we're going to rotate it around out of the paper to form a three-dimensional shape. So it's kind of going to be a cone with a nozzle of some sort, maybe. Maybe this is some sort of engine, a jet or a rocket engine, maybe. So there's our graph. And like I said, we can read the intersections off of the graph, but on your homework, you might run across more complicated kinds of curves. So I put this extra step here of finding the intersections so we can figure out our bounds of integration. And to find the intersections, you of course just set the functions equal to each other and then solve. So in this case, we would have x squared plus 1 equals minus x plus 3. So we can move everything to one side. Since this is a quadratic, we'll have to factor. So x squared plus x, and then we end up with a minus 2 when we subtract 3 from both sides. And then this one factors. We don't even need to get the quadratic formula involved. Okay, so now we can read off the two solutions. X is minus 2 or x is positive 1. Okay. And that's exactly what you would see up in the graph. The intersection over here is at x equals minus 2, and then the intersection on the right is at x equals 1. And finally, we'll put all of this together to find the volume. And maybe one more thing, the parabola is the lower curve, so let's label this one with a lowercase r, and this one is the upper curve, the line, so we'll label it with the uppercase r. Okay, so finally, we set up the integral. We know our limits of integration are minus 2 up to 1. And then we're going to use the formula that we just learned, the pi, and then r, capital R of x squared minus lowercase r of x squared. Now plug in. And you can move the pi to the front at any point because it's a constant. I'm going to go ahead and do that now. Our larger function is the line minus x plus 3. That's going to be squared. And then our smaller function is the parabola. So we'll subtract x squared plus 1 squared. And then work through. Let's see, I guess we might as well include all of the details. So square this out, you'll get x squared minus 6x plus 9. And when you square this out, you'll get x to the 4th plus 2x squared plus 1. And then simplify, just combine like terms. Our biggest power of x is here. It doesn't have any like terms, so we just have minus x to the 4th. And then we have two x squared terms. Combine those to get a negative x squared. And then we have a x term, minus 6x. And then the constant term, 9 minus 1, is plus 8 overall. So now we've done, I think, all of the hard work. We did the geometry further up here, and now we have the integral in a convenient form because we can just use the power rule at this point. So increase all of the exponents by 1 and divide by the new exponent. So we have minus 1/5 x to the 5th, minus 1/3 x to the 3rd, and then this one will be dividing 6 by 2. 6 over 2 is 3. Or maybe I'll just write it 6 times a half, x squared, and then plus 8x. Okay. And then we still have to go from minus 2 up to 1. So plug in the two numbers, find the difference. So this is the part where you would have to deal with a few fractions, or maybe go find a calculator. And I think I'll just leave that part off, since that's not really calculus. So once you plug these two numbers in and subtract, you'll get 117 pi over 5. So that's the volume of this three-dimensional object once we rotate around the x-axis. Any questions over that example? And please, if you do have questions, just speak up. Otherwise, we'll move move along to our last example here. So this time we're going to find the volume, well, mostly similar to the last one. Find the volume of the solid generated by rotating the region, bounded by two curves, y equals x and y equals x cubed, about the y-axis. So this last little word here is the primary difference from the last example. Instead of rotating around this way, around the x-axis, we're going to be rotating around this way, around the y-axis. So this is something that we saw last time when we were talking about disks, and we'll also need to think about different kinds of rotations with the washer method. Okay. So the first thing, as before, is to sketch the two curves to start making our graph. Y equals x, that is the line through the origin with slope 1. Okay. So just connect these two dots, the origin and the point 1, 1. And then go ahead and graph the this cubic function y equals x cubed. And what you should remember about y equals x cubed is that it looks something like this. So it flattens out as you go into the origin and then becomes steeper. Like this. That would curve off that direction. Okay. So what we can see from the graph is that the cubic function is actually the smaller function in this region that's formed here. And let's see, let me add one comment here. So if I continue drawing down this direction, we would find another bounded region. Really, in my note up here, I should say the region in the first quadrant, just to specify that we're only going to look up here in the upper right of the plane. Okay, so before we were making slices like this. So this would have been my upper function. This one would have been the lower function. I would subtract the smaller one from the upper one, and we would be rotating around this way. But since we're rotating around the y-axis, this is going to look a little bit different. Our slices are now going to go across this way. And we're going to form discs, not discs, we're going to form washers because they have a hole in the middle this way. So this function, when we rotate around the y-axis, is actually the larger function because it has the larger x value. So maybe we can say it's larger function in the x direction. And when we're rotating this way, that's what matters. So y equals x cubed is going to be my larger radius, and y equals x is going to be my smaller radius. So we've talked about integrating in the y direction before. I think I wrote it down this way. So we're going to be making cross sections in the y perpendicular to the y axis like this. So that's why I've written it as a function of y. And we're going to integrate in the y direction. So that's why there's a dy over here. And now all we have to do is find the area of our cross sections, but these are just the disks again, like before. This should be an r of y. And this is a little r of y, lowercase r. So one problem you might notice is that this integral has y's in it, and my formulas all have x in them. So what we're going to have to do is rewrite these in terms of y instead. So y equals x, just turn it around, and we'll say x is equal to y. This other one, y equals x cubed, we'll have to take the cube root of both sides to get y equals the cube root. R of y equals the cube root of y. So you have to solve these to get these radiuses. Maybe I should make a note here that these two should be solved for x. Because we're looking for a distance in the x direction. And I guess now we should just continue on with our integral. Our limits of integration in the y direction, we can again find by doing an intersection, or we can read them off this graph. We're going to start at the origin at 0 and then go up to 1 where the line crosses the cubic. Okay. And then we need pi times uppercase r of y squared minus little r of y squared. Because we're still subtracting the smaller area from the larger area, we just have y's instead of x's now. And then plug in. So we have a cube root of y for our outer function, our larger function. And that's going to be squared. And then our smaller function is just y by itself. And now that we have an integral set up, this is straightforward calculus. Maybe start by pulling your pi to the outside, and then taking care of these exponents. The cube root of y squared, you probably want to think about the cube root of y as y to the 1/3. And that way you can just multiply by 2 when you have this exponent on the outside. So that's y to the 2/3 power. And then here we have just a y squared. And then let's see, how much time do we have? A minute. I think we can finish this off. So increase the power by 1, divide by the new power. So this becomes 5/3, and we end up dividing by 3/5. Or multiplying by 3/5 when we divide by 5/3. Excuse me. And then we get a 3 in this one. dy. Oops, not dy. Now we need the vertical slash notation, 0 to 1. When we plug in 0 into this, we're just going to get 0 here and 0 there. So we don't have to worry about that one. We'll just plug in 1. And then we would have a minus 0. And then just simplify. 1 to any exponent is 1, so it's just 5/3 minus 1/3. 3/5 minus 1/3, excuse me. I keep on saying that fraction backwards. So find a common denominator and subtract, you get 4 pi over 15. Okay, any questions here at the end of class?
Yeah, what was the answer to the first example?
It was 117 pi over 5.
Thank you.
You're welcome.